Right, last part, part D. At what time t between 0 and 120 is the amount of water at maximum? Right, so we're dealing with an interval here from 0 to 120, and we're trying to find an absolute maximum. So we need to keep in mind could be the endpoints. Right, absolute maximum could be the endpoints. But to find the maximum, we need to look at the derivative, figure out when the derivative is 0. We can look at a number line to figure out local mins and maxes, but then we have to take into account the endpoints. So for this one, let's look at the derivative of the function that we just wrote. Well, derivative of 30 is just 0. Derivative of 8t is just 8. And this last part, derivative of the definite integral from a constant to a variable of a function, is just going to be that function. Right? We've done this before. Derivative of antiderivative, inverses cancel each other out. We just get square root of t plus 1. Right? That's just based on the fundamental theorem of calculus. Now we want to figure out when is this 0. Right? To find our critical values, those points that could be local mins and local maxes. I'm going to add the square root of t plus 1 over to the other side. We can square both sides, and we get t plus 1 equals 64. And subtract, we get t equals 63. So we have one critical value. Now, normally, if we had our calculator, I would probably suggest that we go ahead and check this critical value and our two endpoints, 0 and 120, and plug them into this equation. See what gives us the greatest value. Since we don't have a calculator, like figuring this out, not impossible. We could do it, but it would just take a little bit of time, maybe more time than we want. So instead of doing that, let's think about this. This is our only critical value. So if our function, if this is a local maximum, that means the function is going to be increasing and then decreasing. Not only would that be a local maximum, it would be an absolute maximum, right? It would have to be. If it's just increasing on this interval, then decreasing, that's it. That's going to be an absolute maximum. So if it's a local minimum, we can kind of show that it's also an absolute maximum. If we do a number line for this and we end up figuring out it's it's a local minimum, then we know we don't need to test this. We don't have to plug that in. We just have to check the endpoints. Right? So we can kind of save ourselves a little bit of time, possibly. So let's look at a number line for the derivative. I didn't mark that over here. This is the derivative a of t. So we know when t equals 63, the derivative is 0. If we put something in smaller, like 0, if we put 0 in for t, we get 8 minus square root of 1. Well, that's going to be a positive value. So the derivatives are going to be positive. And then if we look at the right here, if we put 60, let's say 64 in, 64 plus 1, 65. Square root of 65 is going to be bigger than 8, right? So 8 minus something bigger than 8, that's going to give us a negative number. So we know it's a local max, but like I said earlier, if our function is going to be increasing, then decreasing, and that's it, that point has to be the highest. It's going to be higher than both endpoints, because this one had to increase to get there, and then from here to the other endpoint, it's decreasing. So we have an absolute max at t equals 63. Since the derivative of a is greater than 0 for t between 0 and 63, and the derivative of a is less than 0 for all t values from 63 to 120, there must be an absolute max at t equals 63.